Okay, today in this lecture we learn about magnetically coupled circuits. So we have the introduction to magnetic coupled circuits, and we know about the concept of mutual inductance. So first of all, we learn about self-inductance. So we already know the concept that a coil carrying current uh, produce a magnetic flux around it. So that flux is dependent on the number of turns of the inductor. So the voltage or EMF induced because of this flux is in fact is dependent over the rate of change of flux in the conductor. And the voltage or EMF produced is written as V is equal to N d phi by dt. So that's the Faraday's law. So also we know that the flux, the direction of flux is in fact is opposite in the direction of the current flowing into the conductor because the inductor opposes the change of the current. So besides this, we know that the current I, uh, any change in phi is caused by this rate of change of current because the current is time varying in nature. So it's not for the DC current. So it's for the time varying current. And due to this time varying current, we have the change in the flux. So we can say that this induced EMF is N d phi by di, that the flux is because of the change of current, and the current is changing with respect to the time. Or we can cancel di by di, or it is N d phi by dt. So in fact, we want to represent that the current is time varying in nature, and due to the time varying nature of the current, we have the change in the flux. We have the change in the flux. And the induced EMF is directly proportional to these factors. Also, we know that the voltage across the inductor is L di by dt. Now, when we equate these two relations to find the value of inductance, which is L. So the value of inductance by equating these two equations will in fact be L N d phi by di. So this is in fact is the self inductance of the inductor. So that represents by this equation. Now we have the mutual inductance as well. When we have the mutual inductance, when two coils are placed in close proximity or at a very close distance, so the flux of one coil will links with the other coil. So it induced EMF in the nearby coil. So that inductance is called the mutual inductance of the coil. So we can see that there are two networks connected with the inductors. So we want to know that the current source in the first network will induce EMF in the second coil, which is placed nearby, right? So the self inductance of the coil 1 is phi 11, and the the flux introduced in the second coil is phi 12. So this phi 11 is the flux due to the current I1, and due to this current I1, we have also the flux in the nearby coil, which is phi 12. So how can we write the total flux in coil 1? So the total flux in coil 1 is phi 11 and phi 12. Right. So actually this is the total flux due to this current I1 of T in the first coil and in the second coil, and this is phi 1 is due to I1 of T. So we have the induced EMF of coil 1 is N1 d phi 1 by dt, and the induced EMF in coil 2 is N2 d phi 12 by dt. So in fact, the flux associated from I1 current source to the second coil is in fact is phi 12. So we have these two relationships in equation 13.6 and 13.7. So we can also express this equation in forms of self-inductance and mutual inductance. How we can write this? That N1 d phi di1 is equal to di1 by dt, and N1 d phi 1 by di1 is the self-inductance of the coil 1, and this expression V2 is N2 d phi I2 by di1 and di1 by dt, and this is the mutual inductance of coil 1 associated with coil 2. So that is M21. So we will express the value of the mutual inductance M21 is N2 d phi I2 by di1, and we have the value of V2 is equal to M21 di1 by dt. So now you know the concept that just like self-inductance, we can express the mutual inductance of the coil as well, which is M21. So next we see that if we have the current source in the mesh 2, so that has a flux phi 2 which has two components. So that one component is phi 21, which is the flux related from coil 2 to coil 1, and phi 22 is the flux of the coil 2 linked with the coil 2. So that expression is split into two terms. So first we write the value of V2, and this value of V2, is in fact is N2 d phi 2 by dt, and N2 d phi 2 by dit is in fact di2 by dt, or we can write it as L2 di2 by dt. So you can see here that this expression, we have the inductance of the coil, which is L2, and that is L2 di2 by dt. So now we see the EMF induced in the first coil due to the current source in the second mesh. So that is V1. V1 is in fact is N1 d phi 21 by dt, and that is N1 d phi 21 by di2 and di2 by dt, and that is M12 di2 by dt. So this M12 is in fact is N1 d phi 21 by di2. So we have in fact is the mutual inductance M12 expressed due to the current source I2 and its associated flux in first coil, and that induced the EMF V1, that is equal to M12 di2 by dt. So now review what we have learned. So first is in fact is we have seen that we have a current source in the first network with an inductance of L1 and L1, and that induced the EMF in V2, and that has the value of V2 M21 d phi I1 by dt. So M21 is the mutual inductance of the mutual inductance because of this current source I1. So this current I source I1 has the mutual inductance in the coil 2. So the value of this V2 due to this mutual inductance is determined here. Also, we have seen that we have a current source in the second network to link with the second, to provide current to the second coil, and that induce the mutual inductance in the first coil, and that has value M12 N1 d521 by di2. And the value of this EMF induced in first coil is the value of mutual inductance into di2 by dt. So we have the two mutual inductance M12 and M21. So the magnitude of these two mutual inductance are equal M, and the units of this inductance is Henry. So we have linked the flux induced by one coil to another coil with a specially designed core to link the flux of the two coils. Also, there is, in fact, we can see that these two flux, phi21 and phi12, are in same direction. So we know the rule to consider the flux direction in the coil, and depending on the flux direction, the polarity of the EMF induced V1 and V2 will be changed. So phi12 is because of I2 and is induced EMF V1, and phi21 is due to I1 and it induced EMF V2. So we have to consider the dot enter and dot positive rule. So the dot enter and dot positive rule is that we can determine the flux direction by knowing the value of the dots. For example, if we have a dot and the current I1 is entering from the dot, right? So it induced the polarity V2, which is positive for the dot, right? I repeat it again. If the current is entering the dot, right, and we have the induced EMF V2, which is in fact is the polarity positive at the dot point. Similarly, for I2 current, we have the induced voltage V1 and we have the positive polarity at the dot. So that rule is dot enter and dot positive rule. So this convention is in fact is used in electric circuits to represent the polarity of induced EMF due to current I1 and the polarity of current V1 due to current I2. So this convention is called dot convention. So what this dot convention says, so we see here, this dot convention says that if the current enters the dot terminal of the coil, so the polarity of this dot terminal is positive and negative. So the value of the mutual inductance is positive, right? And if we have the current entering the dot terminal, and here we have the polarity of the V2 will be changed. So we have positive here and negative here. So, or we can say that the V2 is minus M d phi I by V2. So the polarity of this induced EMF will be changed in sign if we have the current entering the dot terminal and we have the positive polarity at the dot terminal. So the sign of the induced EMF will be changed. Similarly, in case of current leaving the dot, so the dot is at the point where the current leaves the circuit. So the sign, so the induced EMF V1 in this network has the negative polarity. Also, we have the current I2 leaving the node. So the polarity at the dot terminal is negative, and we have the induced EMF which is positive in sign. So this is in fact is the dot convention rules which we follow in magnetic couple circuits. So we see the example of the network. So this network is magnetically coupled. So we have the L1 and L2 in close proximity and they have the mutual inductance. So this is in fact is the time domain representation of the circuit. So we convert it into the frequency domain representation. So we can convert it into the corresponding frequency domain representation. So all the components are same, but the inductance is just like we have the self-inductance, we have the j omega m instead of the m in frequency representation. So it's clear. So now we see that for this time domain circuit, we have the V1 in the mesh 1 is equal to I1 R1 L1 dI1 by dt plus we have the M dI2 by dt. Why we have the sign of this is positive. Why the sign is positive? Because the direction of the current I2, the direction of the current I2 is entering is entering from the dot point. So the voltage induced has polarity positive at the dot and negative at the other side. So we have this sign is positive. Also for mesh 2, we have the current I2. Now look at the direction of the current I2. The direction of the current I2 is counterclockwise. So it enters the dot point. That's why we have the positive sign here. Now see the direction of I1. I1 direction is clockwise. So it is in fact is entering the dot side, and the value of this inductance is positive, negative. So this is M di1 by dt. So this is M di1 by dt with the plus sign. So I repeat this again because I think it's important that this I2 current induced EMF, which is M di2 by dt. So that is the voltage adds up into V1 due to this mutual inductance, right? And now what about the polarity? So this I2 current enters the dot point. So at the dot side, we have the positive. So that is dot and enter dot positive convention. So also we have the I1 current, and that I1 current induced the EMF M di1 by dt. So this is also the dot enter and dot positive convention, and the value of this is M di1 by dt, right? So this is the time domain representation. Now we consider this circuit for the frequency domain representation. For the frequency domain representation, we have the same convention to follow. So it is the dot enter dot positive convention by which we have the value of j omega m I2 is added into V1 and j omega m I1 added into V2, right? So this is in fact is the magnetically coupled circuits in which we have applied dot enter dot positive rule for to find the value of V1, V2 in time representation, and in phasor representation we have find the value of V1 and V2 in this form. Now we solve a problem. Now we have to find the value of the phasor currents in the frequency domain representation of the circuit when these two circuits are magnetically coupled and the value of mutual inductance is J3 by J3 ohm. Now we see the direction of the current. So it is in fact is dot enter and dot positive rule here. So we have the polarity plus here and minus here, and J3 into I1 is the mutual inductance introduced here. And this is the dot, this is in fact is the dot lead. And we have the negative polarity at the dot. So we have the negative polarity at the dot, and we have the value of minus J3 I2 here. So we do here, the value of this is minus J3 I2 here, because the direction of current I2 is dot lead. So the polarity of the dot is negative. Dot leave, dot negative. So this I2 current is leaving the dot. So we have the polarity of the dot is with the negative sign. And this I1 current is dot enter. And the polarity of this is plus J3 I1 and minus. Now we define the value of the mutual inductance. Now we write the equation, KVL equation for mesh 1 and mesh 2 associated with coil 1 and coil 2 respectively. So for this we have seen that we have minus 12 because the polarity of this current is negative to positive. So we have minus 12 plus we have minus J4 and plus J5 I1, and we have the polarity of this is negative to positive. So we have minus J3 I2 is equal to 0. So we have the value of this equation is Ji1 minus J3I2 is equal to 12. Similarly, we write the equation for coil 2. So here we have a minus J3I1 because of the negative sign or the negative polarity of the mutual inductance. And next we have plus J6 and plus 12, and we have J6 plus 12 I2 is equal to 0. Now we take the value of I1 from this equation and substitute back into equation 1, and we will get the value of I2, which is 2.91 at the angle of 14.04 degrees. So we substitute this value of I2 in here, and we will get the value of I1, which is 13.01 minus 49.39 degrees. Now look at another example. Here we have to find the voltage V out of the circuit, but again it's a magnetically coupled circuit, and the value of the mutual inductance is J1. Now we apply the dot enter dot positive and dot leave dot negative rule. So this I1 current induce a voltage here. So this I1 current enters the dot point, right? So it induced the EMF is equal to J1 I1 here with the positive polarity at the dot. So now the we have the positive polarity at the dot. So this we have the positive polarity here because the dot is not here. So we have the positive polarity of the dot here and negative polarity here. And also we have due to this I2 enters the dot. So we have the positive polarity of the dot here and here. So that is J1 ohm I2 polarity with positive at the dot and minus at the other side. So now you see here that this two currents both have the dot enter and dot positive rule, but in fact the both uh, currents are entering the dot point. So the polarity at the other side of the dot is positive. So due to this I1, we have the positive polarity of the dot here, right? Because dot is here. So it's dot enter and dot positive. And this I2 is enters the dot. So we have the positive at the dot and negative at the other side. So this J1 is in fact is J1 I2 and this is J1 I1. So I hope you understand the concept that how to calculate the induced EMF due to this mutual inductance by using dot convention. So this JI2 is in fact is with the positive sign here because the current is going from positive to negative. And also the current is going from positive to negative. So the value of this mutual inductance is JI1. So we can able to write the equation for mesh 1 and mesh 2 associated with coil 1 and coil 2. So now we can simplify the relationship for the value of I2. So after calculating the value of I2, so the only thing which we need to do is we need to multiply it by 10 ohm, which is the value of the resistor. So this I2 is multiplied by 10 and we will get the value of Vout. So the so far you have learned that we have the mutual inductance in the inductors which are in close proximity, and we use the dot convention to find the value of polarity of the induced EMF associated by the neighboring current, and we can solve different circuits which are magnetically coupled. Now we will see the series connection. So if the two inductors are connected in series, so there is a mutual inductance which is in fact associated with these two coils. And here we also use the dot convention. So the current is entering the dot and the current is entering the dot for the both coil 1 and coil 2. So we know that the self-inductance of the coil 1 is L1 and the self-inductance of the coil 2 is L2 and the mutual inductance of each coil is M. So in fact, this type of series connection is called series aiding connection. And series aiding connection, the total inductance is L1 plus L2 plus 2 times of M, right? Because the magnitude of mutual inductance of the two coils is same, so it is plus 2M. And there is a series opposing connection as well. Series opposing connection as well. The current is entering the first coil at the dot point and the current is leaving the dot point of the other coil. So in this case, the mutual inductance is opposing. So L1 plus L2 minus 2M is for series opposing connection. Now we see this in circuits. In circuits, we have the value of mesh current. I1 and I2 is unknown, and we have the mutual inductance of this J6 ohm and J8 ohm with in such a way that they both are in fact series aiding because the current is in fact is entering this both the current I2 is leaving from both these dot points. So first we explore these two connections for mesh 1, and for mesh 1 we open these two connections. So this J6 ohm and J8 ohm is in fact is because of the current leaving, the I2 current is leaving. So I2 current is leaving. So I2 current is leaving. So what about this value of V1? So when this is leaving, so we have the negative polarity at the dot. So we have minus positive 2J I2 here. So in the first mesh, we have minus 2J I2 positive here. So we can write the equation for this. So for mesh 1, we have minus 100 due to the current direction from negative to positive, and plus I1, which is 4 minus J3 plus J6 here, and then we have the minus J6 I2 because of this I2 current, and then we have minus J2 I2 in this mesh 1 from due to this mutual inductance, because this mutual inductance is in fact has the direction negative which is opposing the current direction, so that is minus J2 I2. So solving this for I1 and I2, so we will have the simplified form of this equation. Now we see the mesh 2. So for the mesh 2, we know that the current I1 is entering the dot, and we have the positive polarity of 2ji1. So we have plus 2ji1 here, and this is the value of this mutual inductance due to this current I1. Now we solve this. So apart from this mutual inductance, there is the inductance of the coil, which is due to the series aiding connection. So due to this series aiding connection, we have the value of this is J2 into 2I2. J2 into 2I2. Because we multiply this J2 with the plus sign, because the both points, the current is in fact is leaving. Actually, here the current is leaving the both inductance values. So if this dot is here and this dot is here, so it is also the series aiding connection. So that is J2 into 2. And what about this inductance minus 2ji1? So we have this value minus 2ji1 because the I2 is facing the negative polarity. So it is minus J2I1. Also, we solve it for I1 and I2, and we will get the value of this equation. Now we have two simultaneous equations for I1 and I2, and we convert it into the quadratic form, find the value of delta, delta 1 and delta 2, and from this delta 1 by delta, we get the value of I1, and I2, we get the value of delta 2 by delta, and we will get the value of I2. So I leave a practice problem for you, which we solve tomorrow. So this is in fact is your assignment. I have uploaded it on LMS, and I will email the slides to you to solve this problem. And if you have any problem, we will discuss in the next lecture tomorrow, and we will study the energy in the magnetically coupled circuit. So this is all about today's lectures, and we